Hello and welcome back to my channel. Today we're going to be talking about Unit 7, or at least the start of Unit 7, where we are going to be talking about slope fields and differential equations. So differential equations is kind of like the overarching topic of this unit. Slope fields is just like a small part of it. So consider the graph of f of x shown above. Sketch small segments of the line tangent to the graph at several values of x. So reminders, the lines tangent to is kind of that line that makes the slope of our graph and hits at that certain spot. So if I were to do at -5, our line might look something like this. And if I make a really small one, you can't really tell it any differently than what it looks like on our line. It becomes a little bit more obvious when we are at a maximum or a minimum, because we have those zeros, but we kind of have these lines that follow our curve in different spots, like so. So those little lines that we just made to represent the slope of our function is what we use to kind of call what we have as a slope field. The big difference that we're going to be talking about as a slope field is the possible slopes for a function at any x value and any y value. So all of those different plus c values that we may have had before are going to be kind of incorporated into this graph, which makes the graphs kind of look a little bit interesting. So a slope field helps us tell how a graph behaves. It gives us various points on a function and the slope at those various points. So we're going to be doing kind of like two things with a slope field. It's going to be sketching a slope field at indicated points and sketching the solution curve of a given slope field. So if we need to sketch a slope field, if given a differential equation, we can sketch a slope field but at indicated points by substituting in x and y values for the differential equation. So we're literally just going to be plugging in whatever values that we need. One of the things that you may want to know is that for the AP test on our slope field, it will never be an undefined slope. If we do end up having an undefined slope, the two options you have are not writing anything or doing a line straight up and down. Both of those are going to mean undefined for us because that slope would be undefined if it's straight up and down, because it's now not quite a function how we need. That means more y values have x values. There's more than one y value for a singular x value. So consider the differential equation dy over dx equals 2y divided by x on the axes provided. Sketch a slope field for the given differential equation and the 6 points. So one of the things that you're going to notice is they give us this equation. This is our equation for slope. It is dy over dx. And we are given these 6 points. So these points are the points that we want to use. So we have the point 1, 1, we have 1, 0, 1, -1, -1, -1, -1, 0, and -1, 1. And so those are the values that we're going to be plugging in for x and y. So one way to kind of make this easier on ourselves, sometimes I like to make a table. So I have x, y, and then I'm going to add a third column here for dy over dx. Technically, it's a row at this point. So our first x value is any of the ones that we want to deal with. I want to deal with the positive ones first. So I'm going to say my first x value I'm dealing with is 1. My y value I'm going to deal with is 1. So I'm going to deal with this point right here first, 1, 1. And then we're going to find our slope. So our slope equation is 2y over x. So 2 times y divided by x. 2 times 1 is 2, divided by 1 is 2. So I have a slope of 2. So I want to try to make this as best as a slope of 2 as I can. Slope of 1 would be at the origin. Slope of 2, we kind of want to be going towards -1. I know it's a positive 2, so I want to be making sure that my slope is going upwards. So we're having our positive slope when it's going upwards. We have our negative slope when it's going downwards. And if it's a slope of 0, it is horizontal. So our normal slope rules still apply here. We're just finding out what these slopes are individually. Okay, so our next point that we're going to do is any of the other ones. So I have 1, 0, 2 times 0 over 1, which is going to equal 0. So I'm going to put in my horizontal slope. Here. And then the last one on this side, 1, negative 1. So 2 times negative 1 divided by 1 gives us negative 2. So I'm going to do kind of the same thing, but in the negative direction. I have a small little dash to kind of help us out, and it looks about the same as our other one. Okay, now we go to the other side. So we have an x value of negative 1, but we're going to look at 1 first. So 2 times 1 divided by negative 1 gives us negative 2. So it's the same as this one over here. Unless we have kind of a little bit more wiggle room, we just kind of want to do our best to make it look like a slope of negative 2. It needs to be going down. It needs to be steeper than if it's a slope of 1 somewhere else. So we just kind of have to make it our best. Negative 1, 0, 2 times 0 divided by negative 1, still 0. And then our last point, we have negative 1, negative 1. So 2 times negative 1 divided by negative 1, which equals 2. So when we draw out a slope field, it's going to look something like this, where we just have a bunch of dashes in different places. Those dashes represent the slope at those particular points to kind of help us out. So consider the differential equation y squared divided by x minus 1 on the axes provided. Sketch a slope field for the given differential equation at the 10 indicated points. Okay, so here's the deal. They don't necessarily care if you show them all of your work. So that table that we did, we don't necessarily have to do. It's more of just might be helpful to kind of keep things together. So we can do this just to a point at a time and think through what our problem would be. We just have to make sure we get to every point. So if I look here, consider the differential equation on the axis provided. Our differential equation this time is y squared divided by x minus 1. We have x values at 0 and at 2, but nothing at 1 because those would all be undefined because we have x minus 1. So if x is 1, 1 minus 1 would be 0, and we can't divide by 0. So they skipped over that portion. So at 0, 0, 0 squared divided by 0 minus 1, thankfully, is going to give us 0. If I go up, so y squared is now 1. I have 1 squared divided by 0 minus 1. 1 squared is 1. 0 minus 1 is negative 1. So I know the denominator is going to be negative 1 every time because 0 minus 1, as long as I'm in that 0 for x column, we just have to worry about y squared. So 1 divided by negative 1, so it's negative, it's 1. So I want to try my best to go through our point to look something like this. Our next point is a y value of 2. So x is 0, y is 2. 2 squared is 4. 4 divided by negative 1 is negative 4. So I want to make sure that this is a lot steeper than what we did before. It's still negative, just steeper. So I want to make sure that there is a significant difference between a slope of negative 1 and a slope of negative 4. If I go down, negative 1 squared isn't going to change the value. So negative 1 squared is still 1 divided by negative 1. So we have a slope of negative 1. I want to make those relatively the same. And then we have 2. Negative 2 squared is 4, so I have a slope of negative 4 again. So just making it pretty drastic. Okay, now we look at the other side when x is 2. So when x is 2 and y is 0, 0 squared is 0, 2 minus 1 is positive 1, but it's still 0. So we have a slope of 0. If I go up 1, so x is 2, y is 1. 2 minus 1 is always going to give us 1, so the denominator is always going to be 1. 1 squared divided by 1 is positive 1. So something like this is going to be our problem. 2 squared is 4. 4 divided by 1 is positive 4. So I want it to be positive, but I want it to be pretty steep. If I go down, negative 1 squared is 1 still. Divided by 1 is still positive, specifically positive 1. And then negative 2 squared is 4. Divided by 1 is positive 4. And I just want to make sure that it is steeper than 1 and kind of matches what we have before. So we get a function that looks something like this for our slope field. When we look at slope fields at just a couple points, even just 10 points, it's not really giving us a whole picture here, but that is okay. It just takes a little bit more time to kind of think through what we're doing. So while the slope field from example 2 is drawn at only 10 points, it is defined at every point in the xy plane, which x does not equal 1. Describe all the points xy where x doesn't equal 1, for which dy over dx equals negative 1. So when it equals negative 1, we're saying the slope equals negative 1. So our slope in our problem is that equation y squared over x minus 1. So dy over dx is equal to negative 1. So that means y squared over x minus 1 is equal to negative 1. So we want to go ahead and make it so it is not a fraction anymore. We're going to get y by itself. So we're going to go ahead and multiply both sides by x minus 1. So we have negative 1 times x minus 1. If we have negative 1 times x minus 1, it's going to go ahead and flip both the signs. So I have negative x plus 1. And then I can go ahead and flip those around to 1 minus x. I need to get rid of the squared now. So our squared is going to give us the square root of 1 minus x. But we do care about this plus or minus because the positive version and the negative version will make a difference. So at any point on the xy plane, where x does not equal 1, and y equals the square root of 1 minus x, or y equals the negative square root of 1 minus x, then our slope, dy over dx, is equal to negative 1. So even though we don't get a specific answer x, y, these functions give us those values. So anytime y is equal to 1 minus the square root, or the square root of 1 minus x, then we know our slope is going to be negative 1. And that's for the positive square root of 1 minus x or the negative square root of 1 minus x. So both of these are making these curves, making these slope fields. And then the other piece of this is that we need to sketch solution curves. So there's a couple things to know with solution curves. The solution curve must be a function. So when we do a solution curve, if we have multiple y values for a singular x value, we are going to have an issue. This is what we call the vertical line test. So if I draw a vertical line anywhere on my graph, I can't have my function go through it at 2 different points. So it has to be a function. The solution curve must be continuous. If there are any vertical asymptotes or other undefined values, our solution curve will stop. So we stop at any holes, any asymptotes. The solution curve must pass through our indicated point. So really make that point super obvious, which you'll see in a second. And when possible, the solution curve should extend to the end of the slope field. Do not use arrows. So if they give you a box to fill in a solution curve, draw the curve to the end of that box, or draw the curve to the end of that graph. If I have to draw a solution curve and I do this, yeah, I might be able to kind of extrapolate what's going on afterwards, but I didn't actually draw a full solution curve. So we kind of want to keep those things in mind when we're looking at these solution curves. So these graphs right here are what we normally think of when we see a slope field. So all of these little dashes are the slope at these different values. We have a lot more slopes here because we have a lot of points that we want to look at, or points in between things that we can look at here. So a portion of the slope field of the differential equation dy over dx is equal to cosine of y as below. Sketch the solution curves through the points 2, 3, and 0, 0. So we have two solution curves that we need to draw. The solution curve at 2, 3, and a solution curve at 0, 0. So the first thing that I want to do is we want to find 2, 3, and we want to find 0, 0. So 3 is about here, 2 is about here, so 2, 3 is going to be here. So I want that point really apparent. So all we're going to do now is we are going to be following these slopes. So if I look forward, so to the right of where my point is, our lines kind of go down, and then they kind of flatten out here. If I look at the other end of this, they go up, and then they kind of flatten out this way. So our solution curve looks something like this. On the other hand, if I look at 0, 0, right here, our function's going to start by going in the positive direction, and we're just following those slopes the best that we can. I want to end it all the way at there, at the edge of that box, and then I'm going to work my way backwards. So I have a negative slope, and it's still going negative, but it's just getting flatter here. So we have a solution curve that looks like that. So we just need to know where our starting point is, and then we want to follow those slopes. A portion of the slope field of the differential equation dy over dx is equal to x over y is below. Sketch the solution curves through the points 0, 2 and 3, negative 2. So 0, 2 and 3, negative 2. 0, 2 is what we're going to start with. 0, 2 is going to be right here. And then we're going to go ahead and just follow those slopes. So if I'm going this way, I can see that my slopes are getting bigger, they're getting positive, and they're going to keep going up this way until we get to the end here. On the other side, it kind of looks like it's doing the same thing. We have positive slopes. We're going to go ahead and just follow these slope dashes until we get to the edge of our box. Our curve would look something like this. Our other one at the point 3, negative 2, so 3, negative 2 is going to be about here, and I'm going to do the same thing. So I'm going to go ahead and follow my solution curve this way. This is an exception to our function where we talk about the vertical line test. This function, we're just going to go ahead and follow our slope on both sides. So we get something that looks like this. This is going to look similar to a hyperbolic function where we kind of have those two pieces. These ones are going to be functions of x. These ones are going to be functions of y. So those are the big ideas of slope fields and sketching solution curves.